Okay, in this video we're looking at chemical reaction quiz number 2. It's going to be on advanced reactions. It has 19 questions. It's worth 30 points and you'll have 45 minutes and link it to complete it for it. So it's just 4 more questions and you have 10 extra minutes for it. So in section 1 we're going to see there are 7 questions that are multiple choice and 1 matching on the basics that we've been going through. So with number 1 we saw that what is the coefficient of the second reactant for it. So we'll see our second reactant is right here because our reactants are on the left side. If we're looking for the coefficient, we would see that it's a number in front, which would be 3 for it. Now our second one we're looking at is what is the state of matter. So we're looking for whether it's an S, L, A, Q, or G for it. And we're looking for our first product. We're going to see our first products right here. We look for the parentheses behind it and we would see that it's S, meaning that it is solid for it. Now our next one we're going to see is what is the name for the first reactant. So we find our first reactant right here and we see the symbol is Al, so the name would be aluminum for it. And then we're asked for the second one, what is the printed subscript, aka the number of the second product. So if we take a look at our second product, the number that's printed as a subscript would be 3 for it. Now, why do we balance chemical reactions? Fill in the blanks. It's so that the reactants actually equal the products, proving the law of conservation of mass, meaning that matter can't be created nor destroyed. So the whole idea is that we want our reactants to equal our products, and that's why we add those coefficients. Now, you are in lab and you add 2 clear liquids together, all of a sudden it begins to bubble and emit heat. Is this a physical or chemical change? And this would be a chemical change because we're forming something new. Emitting heat, light, odor, and bubbling is key changes for it. Now if I said I had a Bunsen burner and a test tube and it started to bubble, I added in that heat, that would be a physical change, whereas if heat is coming off of it with none added, that's a chemical change. Now this one says translate the first reactant for the following equation. So we're translating dicarbon hexahydride for this combustion reaction. So what we need to do is look up what is di. We'll see that di is 2 and then carbon is going to be C. Now remember our prefixes come before when they're in the word form, but they're in our number form, they'll be on the back end of it. So then we find hexa. Hexa means 6 and hydride is H. So we're going to have C2H6 as our hydrocarbon for this combustion. Now how many total oxygens are in the product? So remember that our reactants points to our products, so we're only looking at this side. And we're going to see that oxygen's in 2 spots, so 2 plus 1 would give us 3 oxygens for it. Now, section 2, we're going through our 5 different types of chemical reactions. The bulk of the questions will be about that, and that they're all multiple choice for it. So our options are synthesis, aka coming together, A plus B yields AB, decomposition, which is breaking apart, AB yields A plus B. Our combustion always has the same 2 products, CO2 plus water. Our single replacement is A plus BC yields A with C, B by itself, and then our double replacement is A plus CD, 2 couples leading to AD plus CB. So if we look at this reaction, we actually have a hydrocarbon, we have our fuel as O2, and then we have these same 2 products. So we would see that this one would be a combustion reaction. It may look like a single or double replacement, but there's no replacing. O actually bonds with the C, and O actually bonds with the H2. Now classify this reaction. So what we're going to see is that Al represents our A, Cl is my B, plus my C. So now that C is with B, plus A is by itself. So you would see that this is a single replacement because just 1 switch, and we have a single element on both sides. So with this single replacement, can sodium replace aluminum? If we take a look here, we want to put sodium, and can it go down and replace aluminum? Yes. Remember, a higher can replace a lower. So yes, sodium can replace. This reaction would occur, and we saw it in our previous one. Now predict the missing product for this single replacement. if we take a look at our A's and our B's, we'd see that Li is my A, and now Li is with Cl. We had K as my B, and then we have Cl as my C. Notice that A and C are together, so that means the only color that we don't have is my B, and that would be my K. Now classify this reaction. Notice that we have PbCl2 plus AgNO3 yields PbNO3 and AgCl. Pb would be my A, Cl is my B, Ag is my C, NO3 is my D, and then it yields for what we have. Pb is A now with D plus C with B. So this would be a double replacement because we have two swaps. Pb has a new partner and so does Ag. Now when we're doing those double replacement reactions, would we use a multiplication table? No way, we're not multiplying. Would we use a metal activity series like we see over here? Would we use our periodic table, or would we use a solubility table? So remember, when we're doing double replacement reactions, one of them has to be solid, so we can eliminate A and C. Now, a metal activity series would be for a single replacement, so we would see we need a solubility table because we need to see if it's going to be AQ for aqueous or S for solid. Now, what state of matter would magnesium chloride be? So for this one, we're going to plot it out. So we find magnesium, we find chloride, and we would see that this would be AQ, an aqueous solution, meaning dissolved in water. Now, section 3 is our final section, and it's going to be balancing. There are 3 questions. They are open-ended, and you're going to drag and drop the numbers like we did last time. So you'll have 1 through 6, and you'll have to drag it to the coefficients if you need to show it. You do need to show 1 to get full credit. So for this first decomposition reaction, let's find our arrow and draw a line down. Now N is actually in 2 spots, 1 and 2. So we're going to have 2. H will be 4, O will be 3, and then make the same list on the opposite side. So N would be 2, then we have H as 2 over here, and then O is 1 plus 1 gives us 2. So if we notice our N and N look good, then we have a 2 and a 4. How do I make a 2 look like a 4? I need to multiply by 2. So it not only changes H to 4, but it will also change O to 2. So 1 plus 2 gives us 3, and we are now all balanced. We will have to put a 1 and a 1 for this decomp reaction. Okay, now this is the hardest one that we're going to go through. So find your arrow and draw it down. And it says, hint, you might want to keep SO4 together as a group. So we're going to have Fe is 1, Br is 3, H is 2, and then we could say SO is 4. Then we have Fe, Br, H, and SO as our group. So we would see Fe is 2, Br is 1, H is 1, and then SO, we have 4 times 3, that would be 12. So now let's start balancing. Start with Fe first. How do you make a 1 look like a 2? You put a 2. It not only changes Fe to 2, but it will change Br to 6. Now go to the opposite side. How do you make a 1 look like a 6? We'll place a 6. So it not only changes Br, but it changes H. So now they're balanced. Go back to the other side. How do you make a 2 look like a 6? You times it by 3. So we put a 3 here. That's going to give us 6 hydrogens, and then 4 times 3 would give us 12, and we're all balanced for this double replacement. Now we'll put a 1 here to get full credit for it. Okay, our final one. This is a combustion reaction, and I know this because of my same 2 products of CO2 and H2O. Draw my line down. I have C, I have H, and I have O. I have C, I have H, and I have O. So I have 4, 8, and 2. I have 1, 2, and then 2 plus 1 gives me 3 because it's in 2 different spots. So always start at the top. How do I make a 1 on the product side look like a 4 on the reactant? I'm going to put a 4 there. So 4 times 1 would give me 4, and then 4 times 2 would give me 8, plus 1 would give me 9. Okay, so we have an 8 on our reactant, we have a 2 on our product. How do we make a 2 look like an 8? I place a 4 there. So 4 times 2 is 8. 4 times 1 is 4. So 8 plus 4 would now give me 12. How do I make a 2 look like a 12? I place a 6 here, so 6 times 2 is 12. And we are all balanced. We'll put a 1 there to get full credit. So this takes us through our Peardeck review on March 10th. Thanks for watching.